Okay, in this video, we're going to be looking at transformations of secant and cosecant. Now, when I introduced you to the graphs of secant and cosecant, I started with cosecant. And the reason for that is that we started with sine when we started this whole journey. We started with sine, and cosecant is 1 over sine. So I hoped that being a little bit more familiar with sine, it would be easier to explain cosecant. As a way of reminding you, the purple graph here is the sine, y equals the sine of x. It starts at 0, goes up to 1. It doesn't start at 0. One cycle, a stereotypical cycle, starts at 0, goes up to 1, comes back down to 0 at pi, goes down to -1, and then comes back up to 0 again at 2 pi before it starts over. And cosecant is defined as 1 over sine. So if I have a 0 value for sine, 1 over that is going to be infinity, sort of, as we talked about in a previous video. It's not really 0. It's not really infinity, but as we approach 0, we approach infinity. When I get to 1, I have 1 over sine at pi over 2 is 1. Cosecant is 1 over that. 1 over 1 is 1. So they actually intersect here at 1. And they'll intersect wherever there's a 1 or a -1. When I have sine of, let's see, pi over 2 is there. So pi over 4, sine of pi over 4 is the square root of 2 over 2. So the cosecant of pi over 4 is 2 over the square root of 2, which would be that value there. So this is where the cosecant graph comes from. Let's go ahead and hide the sine graph. And I've got another highlighter on here. This time I've added something to this one, but I'll just point out that the highlighter, the highlighted black graph here, is 1 full cycle of cosecant. Remember that since sine has a period of 2 pi, cosecant also has a period of 2 pi, but it's broken up into 2 parts, this part here and this part down here. It takes both of these, though, to make up a full cycle. If I just take a look at the upward facing loop here, then I'm not capturing all of the behavior that I get for cosecant before it starts over again. So I need both of these loops. Again, remember, though, that this comes from sine, and sine has a period of 2 pi, so cosecant must also have a period of 2 pi. Now, we can shift cosecant in the same way as we shifted sine. It looks a little different, but the behavior is the same. If I take, for example, this d value, what it's going to do, if I change d from 0, don't add anything to the vertical shift, to 1 or 2 or 3, it's going to add, or if I go below 0, it's going to subtract from the height of every piece of the graph. I'll put it back to 0 for now. If I change a, then I'm getting a different amplitude. I'm getting a different stretch. Now, notice that when I change a for cosecant, I put sine back in here. And let me change it so that it says a times the sine of x. Notice how the sine of x has an amplitude of 4. Then the cosecant will also have an amplitude of 4. If I hide the sine graph now, you can see the cosecant graph. I find the easiest way to deal with secant and cosecant graph is to imagine filling in the blanks, right? If I imagine filling in the blanks here, then I know this is either a sine or a cosine. The blanks is either a sine or a cosine. So this is either a secant or a cosecant, and the amplitude is 4 in this case. I can see that from here, a equals 4, a equals 3, a equals -1. It always matches the amplitude of the sine that it came from. Okay, let's put the amplitude back to 1. And we've got, let's see, we've done D and we've done A. Let's talk about B. B is going to introduce more copies of a single cycle, more copies of a cycle in the usual period for cosecant. The usual period for cosecant is 0 to 2 pi. The period is 2 pi. And right now we have 1 copy, right? 1 up and 1 down. So when I change B to a larger number, say 2, it's going to give me 2 copies. I'm going to end up with 4 loops. So let's go ahead and do that. B is 2. Now you can see 1 cycle is still highlighted in black. But between 0 and 2 pi, I have 1, 2, 3, 4 loops. The last one we haven't talked about yet is the C value. And C just moves the graph to the left or to the right. Let's put B back to 1 for now. And then let's move C to the right. And we can watch as the graph moves to the left. C is getting bigger, positive, The graph is moving farther to the left. Go back to 0. If I move c to the left, making it negative, the graph will move to the right. The farther I move c to the left, the smaller it gets, the farther the graph moves to the right. As with any of these graphs, I can combine them. Let's make A 2. Let's make B 3. Let's make C negative 3. And let's make D 5. I need to move my graph a little bit. Now, I don't have the whole graph of the sine here. I'd have to show, let me just go ahead and put that in. Dx plus C plus D. And then if I show my sine graph, you can see the missing piece, as it were. If I graph this function, fill in the blanks there, then I can see where my cosecant graph is coming from. Let me hide the cosecant graph now. If I could figure out what the equation for this graph was, then to figure out the equation for this graph, the orange one, I just have to change my answer from sine to cosecant. I'll do that in another video. Okay, so now we've talked about the transformations of cosecant. To talk about the transformations of secant, all I need to do is change this to secant and change this reference graph to cosine, because cosine is 1 over cosecant. Sorry, 1 over secant. Secant is 1 over cosine. And I can put my highlighter back on again, and let's put everything back to our standard, original, untransformed graph. Now, I'm starting at 1, and for cosecant going down to 0, going, sorry about that, going further down until I get to negative 1, and then going back up, and ending at the same height as I started. That's the cosine graph. The secant graph is 1 over that. It looks just like the sine. The cosine looks just like the sine, but sine starts here and cosine starts here at x equals 0. You could argue that this is the sine graph shifted to the left, pi over 2 units. In other words, if I take secant and cosine and shift it, let's see, if I want to shift these graphs pi over 2 units to the left, then I need to add to c until it's pi over 2. I need to know what pi over 2 is. Looks like it's about 1.5707. So now this looks like, actually no, it looks like a cosine graph, doesn't it? So I need to keep going. It looks like an upside down sine graph, rather. I need to keep going. I need to go all the way over here so that it looks like a sine graph. Or I could shift it to, that's shifting it to the left quite a bit. Instead, I could subtract just a little bit, pi over 2, and I have what looks just like a sine graph. If this is a sine graph, then this is a cosecant graph. But see the parts that are highlighted now? That tells me it's a secant graph. Okay, let's put c back to 0. A and b are 1, c and d are 0, and I'm going to hide my reference graph. As before, I can change both a, b, c, and d to get a different graph of, I love the amplitude, a different graph of cosecant. With the amplitude, the graphs are actually moving apart. That's kind of cool. The parts, the loops are moving apart. Okay. So these videos are getting shorter and shorter because you can do the same 4 things, right? You can shift up or down, shift to the left or right, stretch or compress, so that's what the amplitude does, or change the number of cycles you get in a period of the untransformed graph. You can change the period by changing the value of b. Remember, b is not the value of the period, but it helps us determine the period. I think that's really all you need for this topic. What I'm going to do now is make a separate video that discusses how to take a graph and figure out what its equation is. And the answer will be that there are always 2 options. If you have a graph that looks like a sine graph, it could just be a cosine graph that's shifted over. If you have a graph that is a secant graph, it could be a graph that's shifted, cosecant graph that's shifted over. If you have a tangent, it could be a shifted cotangent. So there's always two options. So what I'm going to do in the next video is I'm going to show you a graph, and I'm going to show you all the parameters that build that graph, and we're going to talk through them. And then I'm going to show you a graph without the parameters and discuss how to find the equation just using the graph.